Well, welcome to another exciting night of our flipped classroom. Tonight's topic is exponential and logarithmic regressions. Now, those words might sound familiar. We've talked about exponentials, we've talked about logs, and we've talked about regressions. But we've never done them together with a regression. So, as you've probably guessed, I've got my nice calculator on my screen here. This is 100% on the calculator, so you need to pause it, go get yours. Don't waste your time watching it without having your calculator handy, okay? So let's just kind of throw a few review things out there before we get into it. This, let's say log base 2 of 8 equals x. I want to be very clear that this was our log form, and we have to be able to convert to exponential pretty quickly. Do you remember how to do that? I know it's been a little while, but do you remember? We always said begin with your base. So I'm going to say this is 2 to the x equals 8. I am now in what we call exponential form. Okay, so we went from log to exponential pretty quickly. Some people call it around the world, but some people like to say begin with the base. Okay, so 2, this is my base here. Those bases stay the same, and then those two kind of flip spots on you. Another thing we talked about was exponential growth and decay. We said a times 1 plus or minus the rate to the time. Okay, it was growth if we had a plus sign here. It was decay if we had a minus sign here. All right, so keep that in mind. If I said y equals 5 times 1.03 to the t, you should be able to tell me if that's growth or decay. Well, since this number is bigger than 1, remember it's 1 add or subtract, because it's bigger than 1, I know it's growth. Okay, to get my growth factor, I take whatever number I see and I subtract 1. So my growth factor is 0.03. Okay, which tells me the rate is 3%. And lastly, the other thing you're going to see in this video that we've talked about a little bit is the word log. Okay, and we said this is called a common log. And there was something special about common logs. Common logs had a very special base, and I want you to put that in your notebook. Common logs had something called base 10. Okay, now there's a second type of log that we talked about right towards the end of break there, and that was called our natural log. Okay, and some of you kept thinking it said IN. Natural log is actually LN, okay, log natural. They pronounce it natural log though, LN. And it has a separate base. It does not have a base of 10 like a common log. It actually has a base of E. And you're going to start to see this number E quite a bit. Okay, E is actually an irrational number. Okay, very similar to, perhaps you've heard of pi, I assume. Pi is 3.14159, blah, 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 blah. It goes on forever. E is very similar. And this is just a button on your calculator. If you hit your second division sign, you will see E. And if you hit enter, you'll see that the E number is 2.718281, blah, blah, blah. Okay? But don't be surprised if you start to see that, more and more often. So the first thing we want you to put in your notebook is this term exponential. And we've talked about exponential for it feels like about 3 weeks now. And the key that we want you to understand about exponential is that the growth accelerates over time. So let's get that definition boxed in there, maybe put a box around it or a star there so we know exponential means your growth is going to accelerate over time. Exercise 1, so again, let's label this. The population of Jamestown has been recorded for selected years since 2000. The table gives these populations. So you'll notice we have a year and the population. Part A, using your calculator, determine a best fit exponential equation. So that's the first thing I'm going to highlight. In the form y equals a times b to the x, where x represents the number of years since 2000. I'm going to highlight that as well. And y represents the population. Round your a and b to the nearest thousandth. Now, there's two bear traps in here. First of all, you have to be smart enough to read this and say it says exponential, not linear. We spent a lot of time earlier in the year doing linear regression. This time we're doing exponential. The second bear trap is the year. And let's highlight that again. It says x represents the number of years since 2000. Well, you're not going to type 2002 in if x represents years since 2000. So on your table in your notebook, I want you to cross off 2000 and think about what would you put there? How many years is that since 2000? I would actually put a 2 there. I would cross off 2004, put a 4, 5, 7, and 9. And again, they tell you that. You just got to read carefully. X is the year since 2000. All right, so grab that calculator, and why don't you jot these steps down? It's been a while since we've done this. You go to Stat, and then hit Edit, and you're going to type these in L1 and L2. Now, if for some reason you don't have an L1 and L2, maybe you need to use 2 and 3, but just keep that in mind. Again, to clear this out, you would just go to L2. Do not hit Delete. You hit Clear and Enter, and it will clear anything out in there. Go up to L1, Clear and Enter, and it will clear that out. So once we've got this typed in, we're carefully going to go back to Stat, arrow over to Calc, and this time be careful. Remember, we need an exponential regression. And I've printed a bunch of my screens. You can see my exponential here looks like it's on 0. If I scroll down, I have to look for EXPREG, exponential regression. And then don't forget to do L1, L2. Now I'm using L1 and L2 because that's where I stored my stuff. If, for example, you didn't have an L1 and you put it in 2 and 3, that's what you would put here. And then it should spit out the exponential regression for you. And they say write that down rounding to the nearest thousandth. All right, so I've got my equation copied down. Notice it's in the form of a times b to the x. It should be different from linear. That's the a value times b raised to the x power. Part B says sketch a graph of the exponential function for the years 2000 to 2050. Label your window and your y-intercept. All right, so we're going to make a nice table here, or graph. I'm going to label my x value as my years, and my y value as my population. Now, all you have to do is read that table. This is my x, the years, the y was the population. So again, I'm going to use 2, 4, 5, 7, and 9, and I'm going to count by 2s, that means. For easier for me, if you want to count by 1s, that's fine. So I'm going to go 2, 4, 6, 8, 10. Okay, and I'm actually going to write years since 2000 because that's what our x value represented, they told us. Now our population. Notice I go from like 5,500 to 7,400. Clearly I'm not going to start at 0. And I'm probably going to count by, I don't know, 500s. So here's what I'm going to do. I'm going to make a little break, which is fair game. Okay, a little zigzag there. And I'm going to say my first tick mark, right at my zag there, is 5,000. And I'm just going to count by 500. So I'm going to say that's 5,500. Let's see, 6,000, 6,500, 7,000, 7,500, and how far do I have to go? That's probably far enough. All right, and then we're just going to go ahead and we're going to plot those. And I can use my table right here. At 2, I'm at 5564. So again, I'm just going to best guesstimate that, as close as I can. At 4, 61, 21. Now remember, this is exponential, so it should be growing. Let's see, at 5, I'm at 6,300. Okay. Let's see, at 7, I should be at 6,800. And at 9, 7,400. All right, and again, it should be kind of a curve. It's not a line, it's not linear. It should have a little bend to it. There you have it, a nicely labeled graph. All right, now this may take a little review to answer this question. By what percent does your exponential model predict the population is increasing per year? All right, so maybe we just need to review kind of our exponential growth model, our AB to the x. Now again, we talked about this a while ago. I just want to be very clear, so let's get this in our notebook. This first number here is our initial, population in this case. That's how much we're starting with. If your B number is greater than 1, we had growth. And if our B number was less than 1, we had what we call decay. And that told us whether we were increasing or decreasing. That number had to be between 0 and 1, of course. So as I look at this number that's being raised to the x, do I have growth or decay? Well, certainly it's bigger than 1, so I know I have exponential growth. Now remember, the formula was always 1 plus or minus the rate to the time. Okay, that was our formula for exponential growth or decay. So since this is bigger than 1, I know it's growth. And I know my rate, I just take my 1.04 minus my 1, tells me I have a rate of 0.04. Now, what percent is that increasing by? Well, we just take that decimal and we move it 2 places back to the right, and I would say that's 4%. All right, part D for the fun part of the question. It says algebraically determine the number of years to the nearest year for which the population will reach 20,000. All right, so I'm going to basically use the equation I have. I'm determining my year or my time when this thing equals 20,000. So I'm just going to set that equation equal to 20,000. 7.92, 1.04 to the x. And now remember, I have to solve this. And this is what we did probably the last 2 days before break. So if you're a little rusty, we're going to talk slow through it. The first thing we said to do is ask yourself, who is that exponent sitting on? It is only sitting on the 1.04. So I want you to box that in. Those have to stick together. You can't break them up. So your first move is to get rid of this number in front by dividing it over. Okay, remember all those word problems we did? Once you had them set up, I think they were pretty nice. It was the same move every time. Now, when I divide that, I get this hideous number, 3.8775, blah, 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 and I'm going to store that into alpha A. You're going to have to store alpha A. So now I can say A equals 1.04 to the x power. Okay, now this is where logs came in. In order to solve an exponential, and remember it's called exponential because the exponent is a variable, we take the log of both sides. So I'm going to say the log of A equals, when I take the log of this side, that exponent log property comes down in front. So I'm going to get x log of 1.04. And then to get that x by itself, I'll simply just divide both sides by the log of 1.04. Now we talked about using ln's before. If you want to use that ln instead of log, that's perfectly fine. But I use logged in this case, and I'm just going to type that in my calculator. And when I type that in, I get x equals 34.553, and it says to determine algebraically the number of the years to the nearest year. So I would say it doesn't happen right at 34 years, it happens during the 34th year, so I would need 35 years in order to see this happen. All right, exercise 2. Which of the following scatter plots would best fit with an exponential equation? So again, the key word in the sentence is exponential, and we've talked about now for a few weeks, exponential is not a linear, it doesn't look like a line, so I know I can kill that choice. An exponential growth, okay, we said grows very quickly, all right? Okay, so it starts off slow, but it grows quickly. Or we had exponential decay, which means it's going to slow down or drop quickly. So I would say my best example of an exponential would be choice 3. Hopefully you would agree. All right, now we're going to switch gears. We have a logarithmic regression. So again, I would box this in your notebook here, and here's our definition. Grows quickly at first, but then its growth rate slows down. Okay, so exponential just shot up and it was quick growing. This one's going to grow quickly at first, but then it's going to slow its roll. So exercise 3. A corn plant will grow rapidly at first as it emerges from the soil and eventually slows its growth rate. Agronomists record the average height for a particular varietal of corn as a function of the number of days since it was planted. The data is given in the table. All right, so use your calculator to determine the best fit, and here's the key word, logarithmic equation for this data. Express your answer in y equals a plus bl on x form, where x represents the days since planting and y represents the average height. Round both a and b to the nearest integer. All right, so here's where we pause it. We go back to our stat edit and we enter all that in. So you work your calculator and I'll work mine. Now I find this one a tad tricky. You'll notice on your calculator screen, okay, and this is why you need to be using yours right along with us, that they don't actually say logarithmic question. There's something in there that says logistic, but that's not logarithmic. So I want to be very clear, we are never using this logistic in our course. All right, the one we're going to use is it says ln, and we talked about earlier in last week or so that ln can be used with log. Okay, so ln is going to be equivalent to our log in this. So again, let's star that in our notebook. All right, there is no log regression. You have to use ln. And I just want to remind you, ln stands for natural log. Okay, you might be thinking log natural because it says ln, but ln just stands for natural log. And we'll talk more about that later on. So in this case, I'm going to pick, what is it, option 9, I believe. And then don't forget to do L1, L2. So again, I have a screen capture of what mine looked like. You'll get a different form, a plus b ln of x, and ln again is natural log or log equation. And they told us to take a and b and round to the nearest integer. So I'm going to say y equals, let's see, the a value is negative 74 points, nearest integer would be negative 74, plus the b value, so 37 ln of x. Okay, so there's my nice equation. All right, moving on to part B. Sketch the graph of your equation below from the x value 0 to 100. So they're telling you you don't have an option. Your x has to start at 0 and end at 100. And I know it's x because there's an x in between them. All right, so we'll quickly get our grid going here. Now again, I'm not going to count to 100 by ones. I'm going to go by tens. 10, 20, 30. And obviously you can finish your graph. All right, now let's talk some labels here. My x's are days. And my y is my height in inches, so we can get that labeled. This is my days. This is my height in inches. And let's just take a look at our heights. My height goes from 4 to 73. So again, I'm probably going to count by tens. And I'm going to pause it and stick those on there. And then I'm carefully just going to go through and plot everything on the table. So what was that? 8 went with a height of 4. So again, I'm going to say 8 4s maybe there. Let's see, 14. And you obviously pause it, plot your own. And I'm just going to try to draw on the best fit curve that I can. Now you'll notice it grows pretty fast, but then all of a sudden it kind of slows down. All right, so I would say this grows fast. And what I mean by grows fast is if the slope were here, if you were to ski down that, that's pretty darn steep. However, if you were to ski on this, I would say that's much slower. So it grows fast, but then it slows down. That's how I know it's a logarithm function. It starts off by growing fast, but then slows down. Part C. The corn will develop tassels when it reaches a height of 4 feet. To the nearest day, use your model to predict when the corn will grow tassels. Okay, so it will tassel when I equal 4. So I'm just going to set that equation equal to 4. All right, now, think about what your gut tells you to do first. All right, my goal is to get this ln of x term by itself. So I first need to boot this guy to the other side. So I'm going to add 74 to both sides. So that gets me, what is that, 78 equals 37 ln of x. All right, then I need to get this ln of x by itself. So I'm going to move this 37 over, but notice they're attached by multiplication. So the opposite would be to divide it over. So I've got to go 78 divided by 37. And that gets me some ugly number. I'm going to say 2.108 blah, 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 store into alpha a. So I'm going to say a equals the ln of x. All right, now, I'm currently in log form. So I just have to ask myself, what is the base on an ln? Well, we know if it says log, our base is 10. But if I have an ln, my base is actually e. All right? Now, e is just a number like pi. Pi is 3.14159.265. E is similar, but it's 2.718, blah, blah, blah. So we just need to convert from log to exponential. So I'm going to say my base is e raised to the a equals x. Okay, and again, this is old stuff we did on the first day of logs. We converted from log to exponential. And again, I want to remind you, e is a button on the calculator. So I captured my own calculator here so we could find it. And e is sitting on the division side. Notice it's in blue on mine, so I would have to hit second first. So I'm hitting e raised to the alpha a. So again, I'm hitting second e, and I'm getting 8.232. And if I go back and look at that question, it says, to the nearest day, use your model to predict when the corn will tassel. Well, it tassels during the 8th day, so I guess it doesn't actually tassel fully until the 9th day. But it does happen during the 8th day. Now, one other quick piece of advice. Here's a little trick, guys. If you look at your log button on your calculator, and you can look at mine here, or your own, you'll notice there's a 10 on it. And what that means, my 10's in blue, it means log has a base of 10, if it doesn't say. Now, if you look at natural log, ln, you'll notice it has an e to the x button, which means that its base is e. So if you ever forget, it's staring at you on your calculator. All right, part D. According to your model, on what day did the corn germinate, emerge from the ground? Well, this question is very similar to C. Think about this. The y value was our height, and our x value was our time. So the question says, on what day, so on what time, did the corn germinate? Well, what was its height when it emerged from the ground? It had a height of 0. Okay, so I'm just basically setting that equation equal to 0 and solving again. All right, so let's use common sense. We're going to move that 74 over. So I would say 74 equals 37 ln of x. This is together by multiplication, so to get rid of it, boot it out of the way, we have to divide it over. That turns into an even 2, which is nice. Now say to yourself, what's the base on an ln? It has a base of e. So now if I convert to exponential, remember, begin with the base. E to the second equals x. And again, I'm just going to carefully type that in my calculator, e to the second, which tells me this germinated from the ground on the 7th day at 7.38. And again, if I just read the question, round to the nearest day, it happened on the 7th day if I round that. All right, exercise 4. Which of the following would best fit a logarithmic equation? Okay, and these are going to be great bite-sized questions. We're going to have you draw exponential and log. Now, can you find one that looks maybe linear? All right, I would say this one, if I were to connect, looks almost like a line, so I want to say that's linear. Okay, now if I kind of connect these, if I get the idea down, those both, notice they increase, their slopes get steeper. So I would say those two are both exponential. Okay, this is exponential growth because it's going up, exponential decay because it's going down. Now take a look at this last pair. All right, it starts off going up pretty fast. Those slopes are pretty steep if I were to ski, but as I ski, it's getting less steep. So this is my log graph. It grows rapidly at first, it's steep at first, but then it becomes less steep. So I would go with choice 4 as my logarithmic graph. Well, believe it or not, guys, that does it for us tonight. Hopefully we had a lot of review of exponential and log and of some of our regressions. We look forward to seeing you tomorrow. Have a great night.